Okay, so today in class, we were unable to complete a homework question due to the fact that we're trying to listen to your wonderful presentations about your TOK posters. So for this time, and not all the time, but for this time now, I'm going to answer this question with a video, which I'll send to you guys later tonight. So basically, part A, we have to find a bunch of derivatives, well, two derivatives of this function, y equals a e to the kx. So this is a derivative. The first, I'm having trouble here with my Zoom. There we go. The first derivative is constant a e to the kx, and then you have to multiply times k because the exponent of e to the x is not a simple x, but it's a function of x, so it's actually a chain rule. So what we end up with is, well, I think maybe the easiest way to write this would be put the k out in front, and then the rest of this stuff here. And as you can see, the rest of the stuff is none other than your y function. So this is k times y, okay? Now the second derivative is what they want in part 2. So we have to differentiate the first derivative. I'm going to differentiate it right here when it's in that form. So I now have the constant k times a, and then I have to differentiate the remaining part. Let me circle that here in green, e to the kx. And once again, the derivative there is e to the kx times the k, again, to finish off the chain rule. So what do we end up with? We end up with k squared now, e to the a kx. And as you notice, this bit here, this portion here is nothing more than your y, so k squared y. And so we've done the first part of the question. So it says, predict the connection between the nth derivative of y with respect to x and y. Well, it looks like the nth derivative, I'm going to guess, is k and y, and that's because when I took the first derivative, k was to the first power. When I take the second derivative, k is to the second power, okay? And I want to prove that by mathematical induction. So that's my statement I want to prove. Well, the first step is to show that P1 is true. And we've actually done that already, because if you look at P1, whoops, P1 is true. If you look at P1, it really just says y with a 1 up here is k with a 1y. Now the first one isn't the power of 1, it's the first derivative. So this one here is the first derivative. And this k here is not a derivative, but it's just a power. So it's y prime is ky, and that was done above in part A1. So that's done. Now the second step in mathematical induction is to assume pk is true. Okay, so assuming pk of true is true means really to assume that the kth derivative is, oh wait, we just run into a problem. This was not a fair notation wise, we have an issue because the question is expressed in terms of k, which is the k here in the question, and then there's a k, where did it go here, in mathematical induction. So since we've already written everything with this first k, let's leave it like that, and let's go back here, and we'll do what, you know, we're told kind of not to do this. Let's say Pm is true, okay, which would mean that Ym is k to the my, and what we'll show is that Pm plus 1 is true. So the k that we use in mathematical induction, we'll just use m there, okay? So that's what we have for the mth derivative. It's k to the power of m times y. And since we want to, well, if you haven't thought about this, your next step in mathematical induction is to differentiate both sides. If I differentiate both sides, you know, the left-hand side is the derivative of the mth derivative. In other words, it's the m plus first derivative. Now, if you want to write it the way they wrote it, it would be dy to the m plus 1 over dx to the m plus 1. So the left-hand side, if I differentiate that, I get the m plus first derivative. Now, the right-hand side, as it stands here, it would be an implicit derivative, and let's not get into that level of complication. We can just take your function for y right here and write it in terms of x, which is a to the kx. So let me finish that off. So the mth derivative is probably best written as k to the power of m times a e to the kx. Yeah? Let me add another page here because I see I'm out of room. Here we go. And 1 sec to get this back. There we go. And so then if we go back to where we were, let's just do it all together here. If I differentiate both sides here, differentiate both sides, what do we get? Well, we get the derivative of the mth derivative with respect to x. And if I differentiate this side here, well, k to the m is a constant times a e to the kx and times k. When I differentiate this portion here, I pick up a k in the front and as another part of another k constant as I finish off the chain rule. Okay, so what do we get? Well, the mth derivative is the mth derivative is the m plus first derivative. And so that gives us y to the m plus 1 is k. And if we put these k terms together, we get k to the power of m plus 1, e to the kx. And so we get y m plus 1 is k to the power of m plus 1. And this is this bit here is y. And I believe if we look up at the top of what we're trying to prove, right, we've just shown that Pm plus 1 is true. So we can now say, therefore, Pm plus 1 is true. Okay, now, to finish off our proof by induction, we'll say P1 was shown to be true. And since whenever Pm is true, Pm plus 1 is true. So therefore, Pn is true for all n in n. Okay, that's a pretty decent question. I think it's easy once you see that it's just a simple process of differentiating both sides. But if I go back to the question itself, you take a look at it, it's not phrased as an IB question, but this could clearly be an IB question. A little bit too easy on the induction side, but the idea of successively taking a derivative and getting a general rule in terms of n and then proving it by mathematical induction is a typical sort of IB question. All right, see you guys in class.